Solving general chemistry problems. Electrochemistry. Electrochemistry is so very important in our modern technological world, it is worth taking a few minutes to see a few applications in detail. First of all, electrochemistry is a means of creating, delivering, and storing energy. We might first think of batteries. The zinc-copper Daniell cell was the first to find a commercial application. His first cell was built in 1836 by having a copper disc with a central hole in it. An ox gullet, an esophagus, contained a solution of sulfuric acid and a zinc electrode. The esophagus was the salt bridge for the cell. The copper disc was the cathode. He improved on it by replacing the ox gullet with a porous earthenware pot. The outer pot was copper and was filled with copper sulfate. An earthenware pot was lowered into the first pot, filled with a zinc sulfate and a zinc electrode. Now the porous pot was now the salt bridge. This cell quickly became the energy source of preference used to power the American and British telegraph systems. Around 1860, a French inventor named Callot developed a variant that became even simpler to use by eliminating the salt bridge. His gravity cell, or crowfoot cell, consisted of a copper electrode at the bottom of a glass jar, and copper sulfate crystals were poured over the bottom. An insulated wire allowed a connection to that electrode. The jar was then filled with distilled water, and a zinc electrode, a crow's foot shape, was suspended at the top of the water. The copper sulfate would dissolve, but the blue solution would remain at the bottom of the jar because of its higher density. When connected, the zinc electrode would anodize and release zinc ions into the upper solution, while copper ions plated onto the copper electrode. Sulfate ions would migrate from the bottom layer to the top layer, maintaining electroneutrality without a salt bridge. The cell could not be disturbed or the layers would mix, but when properly maintained, it provided a stable supply of electricity. The early adopters were, again, the communications industry to power telegraphy. These cells were replaced with the Leclanché cell, which we'll look at next, but these gravity cells remained in service, especially in isolated sites, even into the 1950s. Still in the 1860s, Georges Leclanché developed a cell that still used zinc for the anode, but now had oxides of manganese at the cathode, which was an inert electrode made from carbon. The anode reaction was the same oxidation of zinc as in the Daniell cell. The cathode reactions were considerably more complex. At least 3 reactions could occur to provide the electron transfer. A 4th reaction helped to keep the battery stable. The cathode always started with manganese dioxide, manganese in the 4+ oxidation state. The cathode reactions can produce 3+ manganese in the manganese oxyhydroxide or the manganese sesquioxide. It's also possible to produce 2+ manganese as manganese hydroxide. Leclanché's original cell consisted of a liquid electrolyte like the Daniell cell. However, he and other workers started to add additional components such as zinc chloride to the ammonium chloride, which increased the cell potential to around 1.5 volts. He added starch to thicken the electrolyte to make it more robust to movement. By the late 1880s, further gelification was achieved by the German Krasner, who added plaster and some hydrophilic compounds. This became the basis for the dry cell, also called the Zinc-carbon battery, and was the first battery to find widespread production and application. His battery got its commercial start when an acquaintance asked for help with his failing electric doorbell. Now, the dry cell was longer lasting, less fragile, and could be installed by anyone. It was a great boost to the electrification of everyday life. Improvements over the decades produced batteries with longer performance and longer shelf life, getting to the nominal overall reaction producing the manganese sesquioxide and zinc hydroxide. A schematic of the typical cell shows a central graphite rod acting as an inert cathode, surrounded by a paste of ammonium or zinc chloride and manganese dioxide. Carbon particles are added to increase the electrical conductance of the paste. The paste is all wrapped up in a blotting paper covering which acts as a salt bridge to allow ion transport but prevent direct mixing of the chemicals. All of this sits inside a zinc can, which is the cathode, which is in turn wrapped inside the final outer container. Metal caps on the outside allow for connection to the 2 electrodes. A significant improvement to the zinc-carbon cell was achieved in the late 1950s by Louis Urey, working for Union Carbide. The ammonium and zinc chloride made for an acidic environment inside the dry cell, and this shortened its life. Urey replaced the electrolyte with KOH, potassium hydroxide, making the electrolyte basic, or in other words, alkaline. The alkaline battery greatly improved the performance and longevity of the cell, even though the same redox processes were operating, the reduction of manganese dioxide and the oxidation of zinc. In 1980, his battery was renamed Energizer and now, of course, has a pink drum-playing bunny as its spokesperson. The design has changed. Now the zinc is on the inside. A nickel-plated brass pin is the central current collector and functions as the anode. A zinc paste is formed with the potassium hydroxide to fill the inside. A paper-thin separator, a salt bridge, surrounds the zinc paste, which is in turn surrounded by the manganese dioxide and carbon mixture. A steel can surrounds them all and acts as the cathode. The positive terminal is connected to this outer can, while the brass pin is connected to the negative terminal and insulated from the rest of the container. These are the same redox processes that were part of Leclanche's cell more than a century earlier, but paying careful attention to all details of the chemistry has produced commercial cells with performance that has improved by orders of magnitude. These Leclanche cells are found everywhere in our modern technology and present themselves most often in the familiar cylindrical container. Another common design is that of the button battery, a flattened version of the cylinder. One common chemistry involves the oxides of zinc and silver. Here are the relevant redox reactions. Note how all of the redox active elements are in the solid state: silver and silver oxide, zinc and zinc hydroxide. The electrolyte that completes the circuit between them is produced at the cathode and similarly consumed at the anode, so very little electrolyte is needed, which keeps the needed volume down, allowing for the small size of the battery. The basic structure of the battery, with its zinc anode and silver oxide cathode, is shown here. The storage capacity of these batteries is 6 times that of a comparably sized lead-acid battery. These batteries are used in places that require a small power source, such as hearing aids, watches, or cameras. They've also been adapted for long-term use in such diverse devices as spacecraft and satellites, as well as torpedoes and other underwater vehicles. In the cells discussed so far, they are assembled with the right chemicals, which contain the chemical energy that can be released in a controlled manner with the right device, an electrochemical cell. Once the chemicals have been spent, once the oxidant has been completely reduced and the reductant completely oxidized, we can only create a new cell by assembling new chemicals. Such a cell is referred to as a primary cell. Other types of cells are possible. When these cells have released their chemical energy, they can be recharged by applying an external potential that can drive the reaction in reverse. The chemistry and the physical design permit these batteries to be recharged. They are called secondary cells. The nickel-cadmium cell or the lithium-ion cell are important examples of these rechargeable secondary cells. Here are some of the important rechargeable electrochemical cells. You may be aware that early automobiles had to be cranked by hand to get them started. The engine has to be turning over to generate the sparks necessary to keep firing the spark plugs. Eventually, small electric motors replaced the hand crank, so that now the starter motor turns the engine over to get things moving. The starter motor runs off a battery. It is only used for the couple of seconds it takes to start an engine, but it delivers a tremendous current during that short time. Once the engine is running, another device called an alternator provides electricity for the engine operation, but also to recharge the battery. The battery found almost exclusively in cars is a lead-acid 12-volt battery. This battery has been in use to start vehicles for more than 100 years. The anode has porous, spongy lead packed into a lead frame, while the cathode consists of lead oxide packed into another lead frame. A separator film keeps the electrodes from touching each other and shorting out the circuit internally. The electrolyte is 35% sulfuric acid solution. Under these conditions, the electrolyte will have a large concentration of H+ and HSO4- as well as some SO4 2- ions. These allow for slightly different reactions, but typically we report them as follows. At the cathode, the lead oxide is reduced to lead sulfate. Lead goes from the +4 to the +2 oxidation state. At the anode, the lead metal is oxidized to lead sulfate. Lead goes from 0 to +2 oxidation state. The cathodes are connected to each other in series and from there to the positive terminal of the battery. The anodes are similarly connected in series and to the negative terminal. The overall cell reaction is this. Students sometimes find this confusing because the lead is being both oxidized and reduced. This happens because it has at least 3 stable oxidation states, 0, +2, and +4. The standard cell potential is plus 2.05 volts. When assembled, a battery of 6 voltaic cells, for the voltage for that is a little over 12 volts, 6 times 2. This battery has 2 features that make it so useful. It can deliver a very high current for the short time needed to start the car. Note that it needs no salt bridge. The redox active components, lead sulfate, and lead oxide, are all solid. They're not in solution, so they can't diffuse directly to the opposite electrode. The separator is there to keep them from bumping and growing into each other. Both half cells use the same sulfuric acid electrolyte. As well as pointed out already, it is rechargeable, so it can be kept fully charged by running the car. Some drawbacks include that it is heavy, given all that lead. Cars and trucks have accepted that its mass is just part of the required overall payload, but using it in other mass-sensitive applications is not viable. Also, long-term use ultimately leads to its failure. The charge-discharge cycles can change the morphology of the electrodes, and they may start to grow little spikes of lead between a cathode and an anode plate, short-circuiting the battery if the separator fails. It can lose or gain water, which changes the potential, and it contains a strong corrosive acid that can make them difficult to work with. Also, all of the lead makes it an environmental hazard upon disposal. They need to be handled correctly. But when done so, they have proven immensely useful in driving the world's transportation expansion of the past century. Another important secondary battery, one that is designed to be recharged, is the nickel-cadmium battery, or NiCad for short. Referring to the SRP tables, you might be tempted to conclude that the redox reactions involving them might mirror those found in the Daniell cell. Just replace copper with nickel and zinc with cadmium. Indeed, such a NiCad wet cell was first developed way back in 1899. However, such a liquid electrolyte cell would make a battery that was inconvenient to use and not at all amenable to mobile applications. The actual redox processes involve the hydroxides of the metals and an alkaline electrolyte, usually KOH, that ensures that they precipitate out as solids on their respective electrodes. The relevant reactions are given here. Note that the standard cell potential is 1.30 volts. The NiCad battery is quite versatile and was the top rechargeable battery for a while. It is well suited for use in portable devices such as electric toothbrushes and construction tools. It is able to deliver quite high currents, better than alkaline batteries, for instance. Here is a schematic of the interior of a NiCad battery. Note how the cathode and anode are formed as long sheets and wrapped around each other in a spiral. A separator sheet keeps them insulated while providing for ion motion, as they do act as salt bridges as well in this case. The wrapped electrode structure provides for a very large surface area, which permits a larger current. Perhaps the most popular battery these days is the lithium-ion battery. Lithium is the lightest metallic element in the periodic table, and such batteries are substantially lighter than most others for the same amount of stored energy, especially when compared to the heavy lead-acid battery. The lithium-ion battery has taken over much of the portable power market. There are many variants of the chemistry of the lithium-ion battery. Most of those variations deal with the design of the cathode. The anode, the negative terminal, is most commonly made from carbon in the form of graphite. Lithium ions are able to move into the graphite by sliding between the atomic layers in a process called intercalation. Graphite is able to accommodate 1 lithium ion for every 6 carbon atoms, forming the intercalation compound described as lithium hexacarbide. At the cathode, the positive terminal, the first commercial product which has remained widely used, was lithium cobalt oxide, LiCO2. The relevant redox reactions are given here. During discharge, the electrons, as always, flow from the anode to the cathode. In this battery, the lithium ions then flow from the anode to the cathode to balance the charge. An electrolyte that allows for the migration of the lithium ion from the anode towards the cathode is needed. Some batteries use a liquid electrolyte with an organic solvent containing dissolved lithium salts, such as LiPF6, LiBF4, or LiClO4. Lithium polymer batteries use a polyoxyethylene polymer for the solvent. It provides for more stable, less flammable batteries. Solid electrolytes made from lithium metal oxides are being developed to create even more stable, long-lasting batteries. Development of new cathode materials has centered on different metals in the lithium metal oxide. Lithium iron phosphate and lithium manganese oxide have been adopted for various applications. More recent variations include lithium nickel cobalt aluminum oxide and lithium nickel manganese cobalt oxide. And they have provided improved safety and performance. In each case, the electrochemistry involves one of the transition elements changing oxidation state. The cell potential is in the range of 3.2 to 3.8 volts, which depends upon the specific cathode material being used. These batteries, both primary and secondary rechargeable, are found commonly in everyday technology. The phrase, "batteries not included," is a common alert printed on many consumer products. The next video in the series will look at some newer applications of electrochemical power sources.